So let's take a step back and look at some of the science. Why does the climate get disrupted? Why does it get warmed up when we put carbon dioxide in the atmosphere? So this is because of the greenhouse effect. This is a figure right out of the book. So for those who aren't familiar, let me just quickly explain what is the greenhouse effect. What are greenhouse gases doing? So the sun is shining down on us with lots and lots of energy. I'll even show you those numbers, how much energy that is a little bit later. And that warms up the Earth from the sunlight hitting it. And then the warm Earth radiates that heat back up as what's called long-wave radiation, or it's in the infrared region of the spectrum. Radiates it back up towards space. And if we had no atmosphere with no greenhouse gases, that would just go right back up into space. But luckily for us, we actually do have an atmosphere. We wouldn't be here without it. And the greenhouse gases in the atmosphere trap some of that long-wave radiation. They actually absorb it and send it back down to Earth. And they also send some of it back up into space. That's the greenhouse effect. It's just a blanket around the Earth, basically, capturing this heat that would otherwise be escaping to space. So it's a good thing. If we didn't have those greenhouse gases, this would not be a livable planet. We need them. And what they do is they allow our planet to be, on average, if you look across the entire planet, about 60 degrees Fahrenheit. So obviously in a given location, the temperature varies wildly, and some locations are warmer than others, but if you look across the whole planet, it's about 60 degrees Fahrenheit. If you took away those greenhouse gases, the planet would be about 0 degrees Fahrenheit on average, which would not be very hospitable for us, or many other things. So we would basically be a dead planet if we didn't have those greenhouse gases. You can just look at some neighboring planets like Mars, which has lost most of its atmosphere, and it's not a very hospitable place. Now, what's amazing is that massive effect from 0 degrees up to 60 degrees Fahrenheit is actually caused by a really tiny amount of gas in the atmosphere. So this shows you what our atmosphere is made of. The circle on the left is the whole atmosphere, and you can see it's almost all nitrogen. The vast majority of our atmosphere is made of nitrogen, which is not a greenhouse gas. The next biggest gas would be oxygen, which is very important for us, but not a greenhouse gas. And that tiny little sliver you see there of what's left is what's blown up on the side there. And that tiny little sliver is mostly argon, also not a greenhouse gas. That's just an inert gas in our atmosphere. And only that tiny little sliver of the tiny little sliver is the greenhouse gases like carbon dioxide, and there are some dozen or so other greenhouse gases. Methane would be another example. So it's really a minuscule fraction, 0.05%, less than 0.05% of our atmosphere made up of these greenhouse gases. And yet they have this massive effect on our climate. And what that tells you is that a little bit of greenhouse gas goes a long way. They're really powerful. So you can look at how they can affect our climate by going back in the ice cores, and we saw some of this presented earlier. What an ice core is you go to a glacier, you can go to Antarctica, and you dig down into the ice, and you core it out. You pull out a section, a cylinder of that ice from a nice deep hole. And what that gives you is a historic record of what Earth was like, dating back for a very long time into the past, because what makes up these glaciers and the land ice in places like Antarctica is snowfall every year. You get some snowfall, it gets compacted down, and then the next year it snows on top of that and gets compacted down, and they just build up on top of each other. And so you get layers, and you can see there that in that photograph, the layers, each one of those stratum is 1 year. And what's amazing is that trapped inside that ice is the actual air that was on Earth at the time that snow fell down. And this goes back for hundreds of thousands of years. So there's air that was trapped hundreds of thousands of years ago in tiny little bubbles inside that ice, and it's still there. And so you can dig down, pull it out, and sample it, do some spectroscopy on it, and actually measure what is the composition of that air, how much carbon dioxide, for example, was there in it. You can also pull out what the temperature was from these data, because there's different isotopes in there that allow you to do that. And so we have pretty good data going back much further than I show here. We actually can go back about 800,000 years with these ice core data and show the temperature on the planet and the carbon dioxide in the atmosphere. And those data are shown here from one of these ice cores, and the particular one shown here is the Vostok ice core. You can see here in the red is the temperature, and in the blue is the carbon dioxide. And you don't have to be a scientist to look at those and say they're obviously correlated with each other, right? And that's not surprising. This is what we would expect. Carbon dioxide is a greenhouse gas. You put more of it in the atmosphere, it's going to warm up. You take some out, it's going to cool down. And they've been tracking each other for a long time. And if you look at this carefully, you can see it looks like there's a bit of a cycle there. About every 100,000 years, you get this up and down nature to it, right? So why does that happen? Where does this natural variability come from? And I'll show you that, but first let me point out, look at the scale here for the concentration of carbon dioxide in our atmosphere. The units are ppm, that's parts per million. So again, we're talking about tiny amounts of gas. But you can see the entire history shown here ranges between about 180 and about 300 parts per million. Never went above 300 parts per million in that history shown there, 300,000 years. And in fact, it never went above 300 ppm if you go back 800,000 years, or even longer. That was the maximum, was 300. Keep that in your head for a second. So why did we get these cycles, though? Why does the temperature on our planet change like that? It has to do with something called the Milankovitch Cycles, named after a guy named Milankovitch. And what he figured out, he was actually under house arrest during a war in Europe, and so he had a lot of time to think. And he figured this out, that the Earth changes the way it goes around the sun very slowly over time. It changes the angle, it wobbles around, the shape of the orbit changes. They're not big changes, they're subtle changes, but a little bit can make a big difference. And the time scale of that is tens and hundreds of thousands of years, and that's what causes that cycling that we see in the deep ice core. So even if were never on the planet, the temperature would change, but the time scale of that would be tens and hundreds of thousands of years, not decades. And then we came along. So it was doing that happily between 180 and 300 ppm back and forth for about 100,000 years, and then we started taking this fossil fuel out from under the ground, which has lots of carbon in it that was trapped in the oil and gas and coal for millions of years, and we burn it, and that puts that carbon back into the atmosphere, the carbon dioxide back into the atmosphere that had been trapped all that time. And so we should see that the carbon dioxide concentration in the atmosphere will be going up if we're adding carbon dioxide. And it sure is. These are data taken from Mauna Loa. And you can see that's the carbon dioxide concentration by year from 1960 or so up to the present day. And you can see it just keeps marching up. And it's marching up because we keep adding carbon dioxide to the atmosphere by burning fossil fuels. Notice the numbers, though. Look where we are today. We're at 400 ppm today. That's 100 more than it has been for, in fact, millions of years on Earth. And if you go back to the last time we had this type of concentration of carbon dioxide in the atmosphere, Earth was a very different place than it is today, and not very hospitable to modern society. So this is a big concern, and that's where we are today. That's still going up. So carbon dioxide goes up, temperature goes up. Here's the temperature data. So there's all kinds of different ways to measure temperature around the Earth and aggregate that data, and here's various different measurements of that, and you can see from here shown from 1950 up till today, it's been going up. Anyone who tells you the planet's not warming, there's your data. You can't argue with the data, it's going up. Now it jumps all around for all kinds of different reasons on a short time scale, but on the long time scale, it just keeps climbing. One of the reasons that it jumps around is that the heat that we're adding by putting more greenhouse gas in the atmosphere is not all staying up there. Some of that heat goes to other places. In fact, almost all of it is going into the oceans. The oceans are massive heat sinks. They just soak up heat. So all this heating that we're adding by putting carbon dioxide in the atmosphere, a little bit of it stays in the atmosphere, that tiny little fraction shown up there. But over 90% of it is going into the oceans and warming up the oceans. And there's exchanges of heat between the oceans and the air all the time. And those happen on all kinds of different time scales based on the way the currents are flowing and so on. And that's why one of the reasons you get a lot of this variation from year to year is the exchanges of heat between the ocean and the air. But the total amount of heat just keeps going up because we keep adding more carbon dioxide to the atmosphere. So there's all kinds of evidence that the planet is warming up. I showed you the data of the land surface air temperature, which is the temperature that you and I experience every day. That's been going up, and we can demonstrate that very clearly with all kinds of measurements from all over the world. We know that the ocean heat is rising, the heat content is rising, and I showed you that's actually where most of the heat is going. But there are lots of other things that you can measure and see this as well. The sea surface temperature is rising. The air above the ocean, as opposed to above the land, that temperature is also rising. The troposphere, that's where we live. That's the lower part of the atmosphere. It's where all weather on Earth is in the troposphere. That's warming up. Humidity is rising, which you'd expect if temperature is going up because more water evaporates. Sea level is rising. Glaciers are shrinking. Sea ice is melting. Snow cover is decreasing. There are countless examples to show you that the planet is warming up. This is incontrovertible. So we're in Florida. So I wanted to show you, let me take a step back. I wanted to show you undeniable proof of global warming. This is what a swimsuit looked like in the 1890s. There's by the 1910s. And if we keep marching forward in time, I see a trend here. And we'll stop at 2015, thankfully. So there's your undeniable proof. If you weren't convinced so far, clearly the planet is warming up. Okay, now there's something that we need to get clear. This is one of the biggest sources of misunderstandings with climate disruption. Weather, which is what's outside. Right now I think it's about 88 degrees outside and sunny, which is I guess what it's here most of the time. That's the weather. That's what it is today here. Weather is not climate. They're not the same thing. Weather is what's happening right now outside. You have to average that weather over 30 years to figure out what the climate is. That's how the World Meteorological Organization figures out those normals. When you see the weather report and they tell you what the normal high and the normal low is for a given location, for a given day, that's what they're talking about, is the 30-year average. That's climate. The average thing that happens over that type of time scale. Very easy to get confused. There was a question earlier today about we had this really cold winter. That has nothing to do with it, or very little to do with it. You have to average, if you had 30 cold winters in a row, that would mean something. One cold winter, 2 cold winters, 1 hot summer, those don't mean anything. You have to look over a long period of time to really understand what's happening to the climate. Point number 2, your city is not the world. We're talking about global climate disruption. What happens here in Orlando or in Chicago where I live or anywhere else on the planet is not necessarily representative of the global climate. So we had an awful winter in Chicago, not this last winter, but the one before. It was one of the coldest winters known. And it was caused, in fact, by climate disruption, interestingly enough. But there were people saying, it's so cold, it's this whole cold winter, where's your global warming? We just had to look somewhere else on Earth. It turns out other places on Earth were actually way warmer than normal that year. In fact, 2014 was the warmest year on record. And many of the warmest years on record have been in the last decade or so. So there's really no question that we're warming up. You just be careful not to get confused about what's happening outside now or even this season. You have to think on a longer time scale, and you have to think about the whole planet. And if you don't do that, you end up with a lot of misinformation, like this example. So pictured there is Senator Jim Inhofe. For those who don't know him, he's a Republican senator, US senator from Oklahoma. And he's one of the biggest climate disruption skeptics, one of the most vocal ones. And he walked onto the Senate floor in February and presented a snowball and said, it's so cold outside, obviously the climate isn't changing. So first of all, it was February in Washington, D.C. I'm pretty sure it's cold there all the time in February. But second of all, it wouldn't matter even if it was especially cold that day or even if it was a snowball in April. That wouldn't mean anything about climate disruption because it's just one day. You have to look over 30 years and across the whole planet. What's a little bit scary, by the way, is that's his role in the Senate. He chairs the Environment and Public Works Committee. These are our elected leaders. Okay, so how do we know? So there's no question, I hope, now that we can all agree the climate is being disrupted. The question is, are we sure that it's us that's doing it? So we know that we're burning more fossil fuels, and that's putting carbon into the atmosphere. There's just no question about that. And I showed you that the carbon dioxide is going up. But we can there's a fingerprint that points the smoking gun at fossil fuels. That carbon dioxide that's in the atmosphere, we can do what's called an isotopic analysis on it. Carbon comes in different isotopes. You've probably heard of carbon-14, which is used for dating old archaeological sites, right? Because that's a radioactive isotope. There are 2 stable isotopes of carbon, carbon-12 and carbon-13. And it turns out that plants really like carbon-12. They prefer it over carbon-13. And so plants, when they process the carbon dioxide out of the air, they do photosynthesis, and they grow. They're pulling in extra carbon-12. And those plants die and get buried, or millions of years ago they died and got buried, and those became coal and oil and natural gas. That's where they came from, was plants a very long time ago. So that carbon-12 excess is trapped in that fossil fuel. And so if we're burning fossil fuel and putting the carbon dioxide into the atmosphere, that increase in carbon dioxide concentration we see should have greater carbon-12 concentration over time or less carbon-13 concentration over time, because it's coming from those fossil fuels that have that isotopic makeup. And you can actually look at that. There's carbon-13, that's the one the plants don't like, and it's going down progressively for a long time. That increase in carbon dioxide is coming very much so from fossil fuels. This is just sort of a smoking gun proof of that. But there's more. We also know that if we're burning fossil fuels, when you burn fossil fuels, part of the chemical reaction is that you consume oxygen. So if the increase in carbon dioxide is coming from burning fossil fuels, we should see the oxygen concentration in the atmosphere going down. There it is, it's going down, measured at 2 different places, California and Australia. We also know that if the warming that we're seeing is coming from greenhouse warming and not something else, there are people who argue that the sun's output has been increasing and that's why it's warming. Turns out the sun has actually been decreasing its output, so that's definitely not it. But aside from that, if it's true that the warming is coming from greenhouse warming, nights are going to warm faster than days because of this blanket effect. If it was coming from an increased output from the sun, nights and days would warm at the same rate. But if it's because of a better blanket, a thicker blanket, if you will, nights are going to warm faster than days do, even though they're both warming. And the data shows that as well. What's called the diurnal temperature range, that's a difference between the minimum and maximum temperatures in a day, has been decreasing because the nighttime temperature has been increasing faster than the daytime. You can also measure this directly. You can actually put a satellite in space and measure that long-wave radiation that's coming up off of the surface and see how much you're getting coming through the atmosphere that's not getting trapped by the greenhouse gases. And you can measure that 30 years ago and measure it today and see is there more getting trapped or less. If the greenhouse effect is getting stronger because we're trapping more. And you can see that. You can also get on the ground and look up and measure the radiation coming back down from the atmosphere, being absorbed and reflected back down, and that's also been going up. And there's the data showing that. There are other examples too. If the troposphere warms up, the part where we live, that's where we're trapping the heat, the layers in the atmosphere above there should cool, and we can measure that, and that's happening too. Also, if the troposphere is warming up, it should expand, just like I was talking about with sea level. The sea level is in part rising because the ocean is expanding as it gets warmer. The atmosphere, our part of the atmosphere, is warming, so it should be expanding. That's happening too. The layers above are cooling, they should be shrinking. We're seeing that too. Every piece of evidence you look at tells you that this is what's happening. Greenhouse warming is why it's warming, and we know that greenhouse warming is coming from our burning of fossil fuels. It's us. Despite that fact, that's the science, when you poll the public, it's a little disconcerting what you find. So this Gallup periodically polls the public and asks them questions about, well, obviously many, many things, but one of those is global warming and climate change. And here's a question that they've been asking for a long time about whether people think the effects of climate change have already begun, will happen soon, will never happen, and so on. And what's a little alarming is that despite the fact that the scientific evidence in support of the fact that this is happening and that it is us has been growing mountainous over time, you can see that since the 90s, these poll numbers have basically not changed. They jump around a little bit, but about a third of the people out there think that this is never going to happen, or at least not in their lifetime, even though it's already happening. So there's a disconnect between the public understanding and perception and the scientific facts. You can see it here too. Here was another question about if people are personally worried about climate change. Is this something that they feel they're concerned about? And you see that number jumps around, but it also has not been going up over time. It sits right around 50%. That's going to have to change. What's interesting is to contrast this with what scientists think about climate disruption. So there's this great study that was done by actually a guy who's a friend of mine at the University of Illinois at Chicago, Peter Doran. He and his student, he's an environmental and earth sciences professor, and he surveyed the community, a big survey, and he asked all kinds of people in the public, general scientists who aren't climate scientists, so biologists and physicists and chemists and everything else, and climate scientists. The question, a very simple question, basically, do you agree with the statement that the planet is warming up and that it's being caused primarily by our burning of fossil fuels increasing greenhouse gas emissions? So that's called what's known as like the consensus view. And so the question is, yes, do you agree with it? No, do you not, or are you not sure? And you can see here that he broke down the results based on the type of people he was asking the question to. The general public, as I just showed you also from the Gallup polls, right around 50% of people think this is happening. But the general public has not been sufficiently educated on the topic. If you go to scientists, that number goes up dramatically. But interestingly, if you go to climate scientists who are actually active in the field, publishing papers in climate science, that's that dark bar on the side. Look how high that is. In this one, it's 97%. It's almost impossible to get 97% of scientists to agree about anything. Trust me, I work with them every day. That's amazing. This is like the highest degree of consensus you'll see in a field about just about anything, other than maybe the basic laws of physics. This is essentially everybody. And in fact, that was in 2009. More recent polls actually show higher numbers. It's now 98 or 99% of the active climate scientists who are on board with this. So anyone who tells you there's a debate in the scientific community is just wrong. The people who know what they're talking about all agree. Now, another way you can measure this is scientific societies. So scientists organize themselves into societies based on their discipline. There's the American Chemical Society for chemists and the American Physical Society for physicists and so on and so forth. And these societies are all over the world. And many of these societies have statements about climate change, climate disruption. And if you look at which ones have statements that say this is happening and that it's caused by us, here is probably a partial list. And I've hunted, and I can't find any, not one, that has a statement saying the opposite. So there just simply is consensus. We should stop this charade of a debate. There is no debate. The facts are clear.